Okay, in this example, we're going to differentiate y equals x to the power of x. And before we get involved with our derivative, let's have a look at this function in Desmos. So here's our function, f of x equals x to the power of x. And we can see, not surprisingly, it's taking off our graph paper pretty quickly. It doesn't take long for it to get into some big numbers. And of course, this is repeated exponent work here of this function, and it's usually called a tetration, as you can see labeled here in my Desmos file. Is usually what we refer to this function as a form of a tetration. Anyway, and another surprising thing, mathematicians have assigned a value to, if we sub in 0 here, to get 0 to the power of 0, and our limit work would be indeterminate form, but in terms of the arithmetic involved in this function, mathematicians have assigned that 0 to the power of 0 is equal to 1 in this context. So anyway, there's the graph, and of course we're going to go differentiate it now, and we'll probably come back to Desmos again, and we'll look at least one tangent slope once we find our derivative. Okay, to differentiate this function, we have to be careful of a couple of common mistakes, and the first mistake is interpreting this as a power function, because we see x to the power of something. Well, of course, that power has to be a constant in order to apply the power rule. So one can't simply take the power down in front and multiply it by this existing base with the power minus 1, because our power has the variable x in it. And the other common mistake is, because the exponent has a variable in it, is to interpret this as an exponential function and applying our derivative of an exponential shortcut, which is rewrite your exponential and multiply by the natural log of the original base. And that only works when your base is a constant. So how can we differentiate this? Well, since there's an x raised to another x, we're going to take advantage of a log property to try to access that exponent, and I'm going to tame things down a little bit. So we're going to apply natural logs to both sides, or any log, but of course natural log is the most convenient in calculus. So if I apply a natural log to the left and a natural log to the right, I am allowed to take my power down now, because I'm just relying on power property of logarithms. So we can rewrite this as the natural log of y. Now that power x can come down in front, and we have x times ln of x. And now we can differentiate this function with the logs applied using implicit differentiation, because now, of course, I think it's clear that y is a function of x. So maybe to be 100% clear, that when we differentiate the left-hand side of this equation with respect to x, we have a trapped function of x inside the natural log. So of course that's going to require the chain rule. And then, far more familiar, on the right-hand side, we just have an application of the product rule. So now we can differentiate this function. So if we differentiate the left-hand side, the derivative of the natural log is the reciprocal of the input. And then with the chain rule here, because y is a function of x, we have to multiply by the derivative of the inside. And there's the derivative that we're looking for. And now a product rule on the right-hand side. First function multiplied by the derivative of the second with respect to x, and that's just a plain reciprocal of x, plus second function multiplied by the derivative of the first, and the derivative of x is just 1. So we're going to multiply both sides of this equation by y of x. And I guess we can start to clean things up, but I'll just do a complete rewrite at this point, even with the multiplication of 1 there. So just getting rid of our fraction there, and there's our y of x going right to the beginning of the right-hand side. And now we can just clean up some things. Our derivative here of this function is going to be y of x multiplied by x times 1 over x. X times its reciprocal is 1, and then this, of course, is just going to be the natural log of x. Now, even though we used implicit differentiation, it's probably okay to leave our derivative as a mixture of y's and x's, but remember, we started with a function of x. We had y equals x to the power of x, so we can just do a substitution here to say, you know what, my y prime, and I think we can leave off that of x notation now. Instead of writing y of x in front of these brackets here, We can just remind ourselves what y actually was. What was our original function? Oh yeah, it was that x to the power of x. So here's our derivative, and it's completely in terms of x, which is a little unusual because usually when we use implicit differentiation, we just are kind of happy with however it kind of turns out in the end, whether it's a mixture of x's and y's or not. But it was a pretty easy substitution to go back to an expression completely in terms of x. So if we're interested in a tangent slope, which I think we might as well do since we got our derivative, the hardest part, if I want to evaluate my derivative at a specific x value, and let's pick something pretty easy, let's say x equals 2. So if we sub in x equals 2 into our derivative, our x to the power of x is going to be 2 to the power of 2. And then inside our square brackets, we'll have 1 plus the natural log of 2. So we can rewrite our tangent slope, and I guess we can label this as m, our tangent slope. M can be simplified down to 4 multiplied by 1 plus ln of 2. A bit awkward, but there's our tangent slope, and our point of tangency, remember, of course, was x equals 2. And subbing 2 into our original function, of course, that's 2 to the power of 2. So our point of tangency is at 2 and 4. So let's type this into Desmos, and we'll let Desmos deal with the decimals and whatnot, and we'll see our tangent line graphed at this point of tangency 2 and 4. Okay, so here we are back in Desmos. Let's type in our tangent equation. Remember, of course, we'll use point slope form here. Well, our tangent slope was 4 times 1 plus the natural log of 2, and that is your tangent slope. And of course we have to put that, multiply that by x minus our x value of our point of tangency, which was 2, and then we'll add on our y value, which was 2 to the power of 2. Okay, we might as well put our point of tangency on here as well. That was 2 and 4. And there we have it. We have our tangent line graph, and we can see that matches the slope of our curve perfectly. And our implicit differentiation worked for this tetration, x to the power of x.